would have a more need for this, like, defense against predators that were going to be coming on, like trying to eat them. So that was the sort of hypothesis coming in, and that's what I wanted to test. And so we got a sample size of around 15 individuals, ranging from 3 centimeters to 30. And the first thing I did was kind of just measure them and see the size difference. And this is what we found: is we have right and left spine from 15 individuals, and on the x-axis you see standard length, and on the y-axis you see spine length. And they're both in log axes because we're really wondering about how these different sizes sort of scale with each other. And when you're talking about length, the slope of this linear regression is you're going to want to try and compare it to the isometry, which is when you're comparing length against length is going to be 1. And this is what we found, is that these spines are actually growing isometrically, which is actually quite interesting. You would imagine that the smaller individuals would want the larger spines compared to their body size. But the bigger individuals actually end up having just as large spine-like ratio compared to their size. So that was peculiar, and I wasn't sure why. So I thought, well, maybe there's a reason for the actual structure. Maybe there's a difference in sort of how these spines end up puncturing the material. And so I went and used a material testing system we have down here in the lab. And I wanted to find a substance that I could stab into, that I could compare against across all the different spines and all the different individuals I have, that would be consistent not only in between the different tests, but also a consistent material that you can measure throughout the entire density of that material. And so what we ended up using was silicone rubber. And you can see in these boxes right here that were 3D printed using rapid prototyper. And to kind of account for size of spine, because some of these spines would range, like the largest spine I had was even bigger than the smallest individual fish I had. So you kind of had to give a ratio of the spine length to be able to account for that. So we used the secondary spine shown. That's what I do. There we go. So you can see that this sort of secondary spine acts as sort of like a natural point of interference. And I took measurements to see where that spine kind of lines up, and it ends up being around 75% of this sort of spine length. And that's kind of how I decided about how deep I wanted to stab these spines into. And so I would hook it up, and there's me, not pissing away. But I would hook it up so I would orient these spines to stab straight into this material. And I would be able to measure on this computer right here the sort of stress, like the amount of load required to push it in that given distance of this spine. And I randomly took one spine from each individual, right or left, and we went through 5 trials, and this is what we sort of saw. So on the x-axis, you can see standard length and force on the y, and these are both, once again, in log axes. But the interesting first thing I'd like to point out is that the n became 14 because when I tried to stab my smallest individual, the spine actually snapped and was unable to puncture this rubber. So you can tell that there's sort of a limitation to how well these spines can actually stab. And the other interesting thing about this graph that I see is that force doesn't scale the same way that length does. So you can't think of it as sort of you can't expect the slope of this line to end up being 1 for an isometric value. What actually happens for force is because you're displacing a volume of this spine, it should end up scaling to the 3rd power. And if you wanted to see what that line would look like, that's what you would see if you were expecting isometry. So we can see that these larger individuals are actually getting better or more efficiently stabbing, which is completely the opposite of what I came in really kind of expecting to see. And so you can see that this sort of 1.66 value of this slope is actually allowing for these smaller individuals compared to the larger individuals are much less efficient at stabbing this material. And to sort of recap what we've found so far is that the spines are growing isometrically and the larger spines are more efficient. Why? And there's a couple thoughts you can look at. It's possible that these spines, the aspect ratio of the spines, are changing as they're getting older. And my preliminary measurements of that show that the larger these spines are getting, the actual the more rotund they look. So that doesn't make much sense, but I need to go back and look at the data and kind of do a full measurement to kind of see how that goes. There's a couple other things you can look at. You can also look at how sharp these spines are getting. But when looking at the spines, you can see that the smaller spines are much sharper than these larger spines. So that doesn't explain it either. And there's one other thing I want to go back and look at in a little bit, is I want to see whether or not these spines are compressing laterally. So instead of stabbing into this material like a spear, I want to see if maybe they're stabbing into it like a knife or a sword, and maybe if that kind of helps with the way that it's going through this material. And that's kind of where I want to take this part next. But that's kind of how these spines are affecting a material that they're stabbing into. But we kind of want to look at how these spines themselves stand up to stress. And to do that, I did some finite elemental analysis. So we took 3 different size classes of spines. We took smaller spines, sort of a medium range spine, and we took some large spines. And we went and took them through and micro CT scanned them. And we took those CT scans and we and we took them, look at that button, and we put them into this program called a Mira, where we could create this tetrahedral mesh. And with that tetrahedral mesh, we could move it into a program, an FEA program called FEBio. And with this program, you can kind of orient the spine to show exactly how I wanted to, exactly how I did my mechanical properties. So I wanted to orient the spine, sort of push this spine kind of going up, so that I can apply a nodal force right here at the tip, and see how that sort of displays. And you can kind of take some of these other parts of the spine and fix it so it's not moving. There's a lot of stuff you can kind of play around with this. And that's sort of what I did, is I fixed this part of the spine right here where it's connecting in with the hyomandibular, and this spot right here where it's fixing in with the quadrate. And those bits of this pre-purple aren't going to be moving around. And so I then put the nodal force on this tip right here, and I accounted for the surface area of these meshes by putting a different ratio of force on these spines, so you can kind of compare against the actual size of the spines themselves. And this is what we found. So what we're looking at right here is, this is one spine just been flipped over, so it's a lateral view, and then this is the medial view. So this would be on the inside of the animal, and this is the outside. So if you're looking at this spine, rostral is this way, and caudal is this way, and then this is sort of flipped on the other side. And this is measured in von Mises stress, because we're working with a ductile material. And you can see that where we have this nice red coloration, that's where this force is sort of being like concentrated. And so with the smallest spine, this sort of force that's being applied to the tip is concentrating right there at the tip. And you can see a little bit of this dissipation of stress down this medial side of the spine. But most of it's being like concentrated right there at the tip. And you see that also in the median spine. So you can also see that this is, once again, the lateral view and the medial view flipped over. And you can see that the stress is concentrated right at the tip. And that tells us that if stress is being applied right there, that's where the bone is going to deform or break, depending on what sort of material it's stabbing into. But both of these are completely different to how the larger spine looks. And you can just visually tell how much, how deformed this spine is, even like as it gets bigger. So we can tell that it's definitely not as sharp as it once was when it was a much smaller individual. You can see that it's actually able to dissipate the stress much more evenly. It dissipated across the tip, and then goes all the way down to the base of the spine where it sort of joins in with the pre-purple. And what that sort of tells us is that the smallest spines end up having the highest von Mises stress, meaning that they're going to break more readily if you put a stress on them. And the large spines are going to stand up to that stress a little bit better. To a point, though, because if you end up having these high stress points, you're going to want to break at the tip rather than break at the base of the spine, because you want to be able to keep that whole structure kind of there. And so this makes a lot of sense to end up breaking here at the tip when you're small, so that you don't lose your entire spine as you get bigger. You want to keep that spine with you as sort of protection. And that's sort of where I focused my research. So in the end, we found that we don't know enough about this sort of like how these spines are stabbing into. There's a lot of ecological sort of thought processes you can use when you're talking about why these larger spines end up being more efficient in the stabbing into materials. And if you have any ideas, I'd love to hear them. I have some of my own that I can kind of share, and we can sort of geek out a little bit about why that is sort of happening. But we don't know just yet, and that's sort of what we're trying to look for, or I'm trying to look for. But one possibility that I found when I was doing some SEMs with these pictures is this is a pre-purposed spine. This is the lateral view. So we're looking at this onto the actual spine itself. And something I'd like to point out is this sort of trabeculated bone that's right in here. And you can see it in this bone, like in this picture, how just beautiful that these are kind of following this sort of canal system. And it could be a reason for why these spines are staying so large or so useful as they're getting larger. Is they're used maybe not necessarily all just for defense, but they might have a different reason for being there. And to me, because of these trabeculations are so highly regular, it reminds me of sort of a sensory system, almost like a sort of like a lateral line system where you have a sort of larger canal running the length of the spine and these small canals kind of joining in with it. And that's hand wavy. I don't have any actual research to support that, but it reminds me of that sort of structure, and that's sort of where I want to go with this, find out what necessarily these trabeculations kind of show. And then I'd like to thank a few people, of course, Dr. Summers and Dr. Pagestrand for giving me a lot of assistance in figuring out my ideas, and then also the TAs, Stephanie and Stacy, and then Ian, even though he's not technically TA, he was definitely a very, very large help in allowing, sort of hashing out ideas, and definitely Dr. Dittmark for helping me get sort of my preliminary thoughts down. He was one of the first people I talked to. And everyone in the fish toss, a lot of you guys helped me with kind of being sort of like backwards and just throw ideas off, and a lot of you guys helped me with stats and stuff, like Jonathan McKenzie and John Luke. A lot of you guys really helped me sort of figure out my stats, because I have very little experience in a lot of that stuff. And also Dr. Thomas Kleintek. Without him, I would not have been able to do the FBA. And my advisor back at Santa Cruz, Dr. Rita Meda, without her, I probably wouldn't have come up. So she told me, she just basically shipped me up here. It was like, go do this. And I'm very thankful that she made me do that. So, thank you.
Yeah, so going back to your scaling prediction, that makes great sense. You and I talked a little bit about the possibility that you might expect that force required to penetrate your material to scale with surface area.
Yeah.
Being squared, and I see you settled on volume. I'm curious what your rationale is first, and second, how are you going to, is there some way that you can determine which of those is the better prediction?
Yes, it's a great question. The reason I settled on trying to use volume is because I do understand that with the surface area, you're actually looking at the surface area of the material, affecting the spine, and that's why you would think that it would scale to the second power. I kind of settled onto it a little bit after I talked about atoms a little bit. But the sort of thought process I was using to go for the third power is you're displacing a set, a volume of the spine when you're pushing it. You're displacing all that material by pushing the spine in. And either way, I can see arguments kind of going for both. But the important bit is that even if you're talking about on the scaling for the second power, your slope still would be going in sort of a negative allometry, which is really the main idea that I want to kind of get across, and I still want to be able to go back and figure out and find a great way to measure and see which is the best way to kind of compare them against. And I don't know the best way just yet, but if you have any ideas on like how to like measure that, I'd love to hear it.
It seems like some kind of geometric shape where you can have clear predictions of what the friction effects would be. Yeah, I would think that you could determine it with some of those.
Yeah.
All right, man. Super weird thing. So, after the Revolutionary War, bandits, we in the British used to try and have this weird sort of shape in the set, and stats is how we laid out. Those were banned. I wonder, do you see the same? You see like a triangular kind of process of measurement due to the signs, like more as they age. Maybe that's explaining where you're getting the ease to sort of stab through the stuff without really adding much more to the area of the actual sign.
When I was doing my initial measurements, I wasn't thinking about revolutionary bayonets, but it's something very interesting. That's actually a really interesting thought as to maybe it's
Totally out.
Yeah, it's totally out there, but it's cool. I mean, the information that we're seeing isn't explained by the sort of what I was using to test. It wasn't what I expected to see. So, kind of using some left field ideas could definitely show some pretty interesting stuff. Yeah.
To that, defensively, but also these animals interact socially.
Mm-hmm.
And so is there a possibility that some of this damage or changes that you're seeing are due as these animals get older and come into breeding conditions, that they're interacting with one another? These spines are important.
That is a possibility. It's an interesting thought. I wouldn't necessarily think that it's any sort of like sexual dimorphism, because you see the sort of same size, whether it's male or female, but it could be used for social interactions, and if so, that might be ending up some sort of like sensory system part of it, and it could be a way to sort of like figure out like, because these guys are benthic feeders, they're down at the bottom, and they're mostly, they don't move around much, they're probably waiting for things to kind of come around with them, and having some sort of sensory system near their jaw would definitely help them in finding different individuals of their same species, food, a lot of different stuff. So that's sort of the research where I come
Is it other things?
The prevercal? Not really. I bet they. I mean, I didn't.
Why don't you highlight where it is for
so
she'll know more about how
the prevercal is right here. So it connects in with the hyomandibular right up here and down at the quadrant. The spines are kind of going in this sort of area right there.
Did they see that? Yeah.
When I put there, they might be able to.
But not very clearly. It would be kind of stretched up, but that's an interesting thought. You can do some just visual sensory systems to see how that's sort of, if they can see like objects that are coming at them from that angle.
And if they can, or could, very well. This way.
Yeah. Yeah, dude. That's cool. John, Luke, and then JJ.
So, you said that you had thought of the data thing, but why do you think that this line becomes more efficient? Because it's lost that tip, and generally, the more curved your tip is, the harder it is for you to puncture with the more structurally sound your spine and what you found, but it's also better sound. So do you have any kind of take a wild hand wavy guess?
Wild hand wavy guess as to why? I don't like making wild hand wavy guesses, but it makes me think that there's some ecological stress, that maybe that there's still some sort of either predatory sort of interaction that we haven't really figured out quite yet. Is maybe there's still some large individuals in their area that they're moving to when they're still large, when they become large themselves. That still could be eating them, so they still need that sort of predatory protection. But I mean, your guess is as good as mine as to sort of the reason as to why mechanically these become better at staffing.
I was just going to ask them the species question. Why the great? Like, if I was to think of something I would use for that, I automatically go to something like mom smart cheap specialized in like setting self information, like automatic. I see it on my mind. That's made for great attack. Whereas the great, I mean, like, I assume that there's, I don't know, just numbers or.
The best reasoning behind it was just because of availability of the species. If I was going to do like stabbing specifically and I had plenty of time to go out and get specimens, I would probably do it on antifreeze, which is the buffalo scorpion, which has a really long spine that is crazy compared to their body size. But we just had so many of these individuals and such across a huge size span that it was perfect for sort of doing some ontogenetic study.
That makes sense. I was thinking thought about them.
Oh yeah, these guys have all been stabbed several times so far.
Yeah.
So.
I have a quick question. Hopefully it's a yes or no sort of thing. Or where is on your when your spine broke when you were puncturing? Where did it break?
The small spine?
Yeah. Did it break on the tip?
It broke on the tip, but like it like sort of like crumpled a little bit, and then just like stopped being able to stab into the rubber. So it broke down the tip to the point where like you just couldn't stab it. And I think that it was just wasn't highly calcified enough to actually be able to stand up to any sort of pressure at that size. I mean, this was a really small individual. So.
Awesome. Thanks.
So we actually went right through our break.
Yeah. So we don't have a break.
So we have another 2 minutes for coffee, pizza, and that.
No, I used to take like my baby shower when I was like, oh, I take my shower. Yeah, because I woke up late and I thought I was well, I actually like sitting down when I do my meditation. It's just a lot of work standing and no, it's still so far. I think you can realize that I should talk before reading. I can answer your questions.
I'm saying for
I can't tell if anyone's even looking at this. I hope someone's looking at this. I hope this is working. It seems to say it is. I would have thought there'd be a little conversation thing, but
Not enough.
one of them I crashed by trying to check and see if it was.
Yeah.
That was what that and the moment I went to it, I got the feedback, and when I left it, it crashed.
I got an email from Pat asking if we were streaming, but I have not.
Tell her to go look at my Google Plus page.
Okay. Yeah, now we're going to get behind again. Well, we are behind.
It's moving, we're gonna get started again. So now we have Amber Leeds, Amber Leeds is going to talk to us about burying flatfish. So,
Hi, so as Stacey said, I'm Amber, and I'm going to be talking to you about how the speed of undulations in burial behavior affects the performance of burial fish. So there are a lot of fish that bury. So Ian in the back, he's working on sandfish and looking at how their opercular jetting sort of digs a hole for them to bury in. And then Nick actually wrote a paper on sand lands burying, where they sort of just like bury their heads in sand and wiggle. And this is a midshipman burying. And this guy was so willing to bury that in order to get this shot of him, I had to put plexiglass underneath him. So he was buried. And there's even a sculpin that buries, which really surprised me. But what I'm really interested in are flatfish. These fish that don't even look like fish anymore, that everybody knows buries. If you ask anybody who's seen Finding Nemo, they will tell you that flatfish bury. But there's surprisingly little literature on how they bury. There's a paper in the 60s that sort of qualitatively says, well, they hit their head on the sand about 3 to 8 times, and they do something funny with their fins, and then they disappear into the sand. Which is nice, but I'd like to look at this a little closer. So here is, if it goes, a video of a flatfish burying. So you guys all got that? Now you understand exactly what's happening here. So my eyes are a little bit slower, and I need to slow this down. So I took high-speed video of individuals. I had 5 species that were collected by trawls and seines by the fish class, the invert class, and some RU students. And I filmed them individually in a small tank with a couple millimeters of sand in the bottom. And I also took pictures before and after they buried to compare how much of their surface area was covered in sand. So here's an example of the before and after pictures. So you can see there's a flatfish, and here you can see there's his eyes left out there, and a little bit of snout. So they're really, really efficient at covering themselves in sand. And this is actually not uncommon. In all of my trials, most of them cover about 95 to 100% of their body. One of them was really lazy and only covered 68% of his body. And a couple of them were in the 80s. But most of them are really, really efficient at covering their body. So this is one of my high-speed videos, and just to orient you, here is the rostrum. There's the tail. This is actually the dorsal fin. He's sort of upside down. Here's the anal fin up here. And as he goes,
Hey.
Okay. So as you can see, right now this is sort of a preparatory, like taking a step back. And then he starts banging his head onto the surface, and he's doing something funny with his fins in the back, just like that paper from the 60s said. And his undulations that start in his head go all the way down to his tail. And he's just picking up this sand that's swooping up above him. And as the video progresses, you'll see this sand sort of settle down on top of him, and he disappears under the sand. So this is the part of my data that was very confusing because he disappears really fast. So it's hard to see what he's doing underneath the sand. But the sand settles, and he has disappeared. That looked like it took a really long time because it was high-speed video, but that entire behavior took 1.5 seconds. And those undulations were going at 10 hertz. That's 10 cycles per second. So just stop and think, and imagine yourself wiggling your body 10 times in 1 second. Like that's And this is pretty much what I saw in all the trials. So here we have the species on the bottom and the time in seconds on the y-axis. They all varied at approximately 1.5 to 2 seconds. There was a lot of them that varied in 1 second, or a couple of lazy ones that took 2.8 seconds. That's like forever, right? And the speed of the undulations is actually really quick too. So the entire range is between 5 hertz and 10 hertz. And there were significant differences between species. So if the bars share a letter, that means that those two species are significantly different from each other. So the Lepidopsida bilineata and Saticus sictus both share an A, and so they're significantly different from each other. And those two were actually the farthest, the biggest difference. So those had a P of less than 0.01, and all the other letters have a P of less than 0.05. This, I think, is partly due to low sample size, so I'm not sure how much to trust these statistics. But what's really interesting is that even though they're undulating really fast and they're varying really quickly, there's no correlation between those two. So the faster they go, the faster they undulate, they're still varying the same amount of time. And that's interesting. So then why are they undulating so quickly? Why are they expending so much energy if it's not increasing or decreasing their time to burial? So I tried asking my flatfish, like, can you just slow down your undulations a little bit? They didn't listen to me, so I made my own flatfish. So this is just a silicon oval that I molded, and I tried to attach this to several motors. I tried a servo motor, a stepper motor, and they just didn't go fast enough because these guys go between 5 and 10 hertz, and the most I could push out of those motors was about 5 hertz, so the laziest of my flatfish. So I was talking to Adam about this, and his first thought was let's use power tools. So we use power tools. So this is my setup. We have a jigsaw up on top of this plank, and we took the blade out and put in a metal rod that acted as an actuator that actually undulated my silicon model fish on the bottom. And then I took high-speed video from the side to see what was going on. I also switched out the silicon model for a large dead flatfish and a small dead flatfish, respectively, to see what the effects of shape are. So here is video of my silicon model from the side. And you can see the actuators over here. The waves, the undulations are going all the way to the end of the model. And it's kicking up sand just like we saw with the flatfish. This one is going at 15 hertz. and he buried about 70% of his body. So it's a pretty good burial. And when I plot the speed of the undulations by the percent of the surface area that they buried, you get this really interesting curve where the faster you go, initially, for the first like 15 hertz, the faster you go, the more of your body gets buried. But after that, there's sort of diminishing returns. So the difference between 15 hertz and 16 hertz with regard to how much of your body is buried is not actually that big. You're just wasting more energy. So this suggests that there should be sort of a lower and upper limit to how fast flatfish bury. So I wanted to go back to my live flatfish to see, do I see this same trend? And I didn't, because my flatfish were very, very efficient buriers. No matter what speed they were, they pretty much always buried 100% or 90%, with a few exceptions. So that was disheartening until I realized that the axes are different. So my flatfish were only burying between 5 and 10 hertz. My model was burying between 3 and 30 hertz. So this purple region right here, that is the entire speed range that my flatfish were burying in. And so what it looks like is that the flatfish have found sort of their optimal speed range to bury in, and they just don't go below or above that, which makes sense, because if you go below that, you can't bury. If you go above that, you're wasting energy. But that's not the whole story. So let's look at what we did in this video and see what's going on with the fins. So as he starts undulating, his fins are doing this like flicking behavior. And that's interesting because if undulation is all you need to bury yourself, why are you doing that with your fins? Why aren't they being held stiff to add more surface area? And so I have a few ideas about that, but none of this has been tested. But the undulations that are being used to bury the fish are the same undulations that an upright fish uses to swim forward, except these are on the side. So it could be that there is some sort of force pushing them forward. So if I want to bury right here, then perhaps the best way to bury right here is to put up brakes so that I don't move forward very much. And the only evidence I've found for this so far is that right before they bury, they take a step backwards and they move forward a little bit. But I don't know if that's actually what's happening. They could also be using it to funnel sand to fall over themselves, or create vortices, or just manually flicking extra sand on top of themselves. But what's really interesting is that in these speeds of 5 to 10 hertz, with my model, my silicon model did not do as well, not nearly as well, as my dead fish at the same speeds. And my dead fish at the same speeds did not do nearly as well as the live fish at the same speeds. So that suggests that there's not only a shape factor, but also a behavior factor. And I think that behavior has to do with these, the flicking of the fins in the posterior part. So with that, I would like to acknowledge the teaching staff of the course, and Ian, who's practically teaching staff. The funding of people who helped me to get here, because I would not be here without any of these people. The fish class and the invertebrate class and the RU students, because they're the ones that got me my flatties. And Nick Goodmark, who helped me figure out the laser cutter. Thanks.
Can you use some kind of glass sand so that you can see? Is there any way to do that?
I've been trying to figure out some sort of like transparent sand. Glass sand would be, I don't know, can you see through glass sand?
It's difficult.
It's difficult? Okay.
There's a copyrighted material that's super expensive.
There is something?
It's super expensive. It's optical for some one class, but the depth and accuracy is 300%. So it still creates the optical material.
That was one of the things I was trying to think of. I was thinking of like maybe attaching little LEDs to the fins of the fish so I could see them from down. I ultimately couldn't think of something that really works.
This is kind of a loaded question. Good answer. So, what is the apparent role of the respiratory system during your day you're doing in gym?
Not that I've seen, but it's difficult. So at the beginning of the video, they do take like a breath. They open up their mouths and then they shut their mouths, and then in their mouths they shut the entire undulation, which makes sense because you don't want to be getting a bunch of sand in your mouth and then into your gills and such. So it doesn't look like they're actively like opercular jetting during it. They may be doing it at the beginning. I'm not sure. I tried putting ink in them, or not ink, dye in their mouths right before they buried, but they don't give much of an indication that they're about to bury, and they take a second to bury, and I'm not that fast. So that didn't actually work. So I don't know if at the very beginning they may be doing opercular jetting. I'm not really convinced that they are, but maybe.
Was there any relationship between the differences in shape and
So I didn't really look at that. There wasn't a whole lot of, that's not true. Okay, I didn't really look at the effects of shape. But looking at the model compared to the dead flatfish, that suggests that there is a difference in shape because the flatfish, obviously they have fins and they're flatfish shaped, whereas my model was just an oval. So I think there is an effect of shape, but I didn't look between species to see the differences here.
Sort of along those lines, have you thought about making your silicone model slightly more flat-ish shaped by getting like thinner fins around the edges or something?
I did think of that. I was going to do that, and I just sort of ran out of time. I actually had, yeah, imagine that. I actually had like a really thin model that I was going to cut and add as fins on the sides, but I didn't have enough time. That would be really cool though.
That's why we're casting.
That's my what?
That's why we're casting.
Oh, okay. Any other questions? All right. Thank you.
Who's next? Is that next? John? Oh, Emily, sorry. I just didn't check the list. So next we have Emily Lavelle, who's going to be talking about ventilation in the different gill openings of Squalus sucklidae. Maybe you want to get rid of that. It's a very large file, the PowerPoint is. It's loaded on the computer, it's just PowerPoint is actually, I'm not actually sure the PowerPoint.
Should we use it on Emily's computer?
I think so, maybe if we can get the next person rolling.
Yeah.
Yeah.
Maybe jump in. Oh. Sorry about that. I'm actually a little bit worried about my computer. We may need to.
Just restart it.
No, so it's basically PowerPoint is sort of just like choking on this.
Yeah, restart the computer.
Can you see how that?
It's fine.
Yeah. be a huge fire. Just got a lot of candy on there. Right.
Is yours rebooting?
We can.
You might be able to get.
Maybe we can get. Yeah. We can lift up now. I'll restart it so you can just plug it in.
Huh? This is Twitter, as far as we used to have this 3 or 4 rock stars. Now we've got the opportunity to reach out to a huge community. Many of whom I don't know. I mean, some of these people, Rachel Tell, Match, no idea who that is. So, yeah.
Okay. Oh, here. No. And that was my. I'm not sure if you. Nope. All right, it's back. Computer is fine.
It would have been sad if it had actually killed your computer forever.
I had a presentation almost on my computer one time. It wasn't just machine.
Press X. Oh, not that X.
The letter X.
On the keyboard.
Jonathan, you may have to.
I think you may have come on close.
Oh,
Emily, you're off.
this is looking good. We've dodged a bullet and skipped our next break.
Okay, so hi everyone. My name is Emily Levin and I'm from the University of Quebec at Rimouski, it's in Canada. So I came here at first because I had a passion for fish and especially for sharks. In fact, I am working on dead sharks back at home, and I just wanted to take the opportunity to work with live animals by coming to Friday Harbor Labs. So what's best in working with live animals is that it gives you the opportunity to work on the action that maintains them alive, breathing. Everyone probably already knows that sharks have at least 5 gills opening. They are using these 5 gills opening to expel the water after the respiration cycle. But why 5? Why 5 slits? Do they really need these 5 openings to complete their ventilation cycle? Are they really using them all? So before I begin, let's take a look at the video I made with my study animal. It's the spiny dogfish. So what you can see is that after introducing a bunch of dye just above the spherical, the first 4 slits seem to release a good amount of dye, but the 5th one doesn't seem to be working at all. So let's take a look at these slits and a different point of view. So those lateral views have been taken from the same shark. The dye is still introduced above one of the spherical. So in the first picture, you can see that the first and the second slit are releasing a good amount of dye. The second picture shows that there's also colored water coming from the third slit. And the last pictures, after inhaling a good quantity of dye, you can also see that the fourth slit also expelled colored water. The only problem with this technique might come from the fact that the dye may dissolve with a good amount of water before expelling it. Sorry. The problem with this technique might come from the fact that the dye is slowly dissolved with water when it comes from the fourth gill, just because the distance between this slit and the spherical is bigger. But I have to say that at any time, I've never seen dye coming from the fifth gill, even if I was dropping a big amount of colored water. So the use of dye is obviously interesting just to take, because it gives an interesting look on which slits are releasing water and which one are not. But it might also be interesting to take a closer look on how these slits are actually working in terms of flow velocity. So that's what I did. To do so, I actually used 7 sharks, 7 spiny dogfish that we caught with the trawl. There was, in fact, 6 males and 1 female that were held in 2 big circular tanks at deep, where the water coming from the Pacific Ocean was constantly renewed. So before taking a look on the actual way of working of these slits, I thought it could be interesting to see if there is any differences in terms of external morphology. So I took external measurements on all of the 7 sharks to see if the fifth gill slit was different from the other one. I collect data from these sharks for first the vertical length of the gill slit, the width of the gill slit, and I record the total length of each individual. The total length was in fact useful only to relate the vertical length of the slit, so I could then use the measurement in terms of percentage of the body length. These measurements were made on live sharks, so it's not always easy to work with these guys. I had to put them in a very small tank and take videos to be able to analyze them on my computer and record these measurements on my computer. So each time I was measuring a shark, I had to do it really quickly because the tank was small and I don't want them to get distressed. So with these data, I decided to make a cluster analysis to look if some of the gill slits are slightly different from the others. So it turns out that for both length and width, the fifth gill tends to be apart with a bigger length and a much smaller gill opening. As far as we know, that the morphology of this fifth gill slit is really different from the 4 others gill opening. But these kinds of data don't tell anything about how the 5 gill slits are working. So it would be interesting then to know if there is a real difference in terms of water velocity coming from them. So to compare the flow coming from each of these 5 gill slits, I use a technique called PIV. So that PIV stands for particle image velocimetry. It is an interesting technique that allows you to quantify the actual flow of the water. So the method is really easy. All you need is a big glass tank like this one. You also need a good camera, a laser, and obviously a lot of particles. So after filling the tank with seawater, we use Artemis cyst eggs to serve as particles. So it is important to put enough of these particles in the water to be able to see them move with the actual flow coming from the gills. The goal here is in fact to create that thing. It's a laser sheet. It's a light sheet that's created with the laser placed on the tripod. And it, in fact, allows us to see only one layer of particles moving from the slits. So once the shard stops moving by itself and lay down on the bottom, a camera is placed in a dorsal view, and it is as simple as recording a short video of a couple of cycles of ventilation. So I have this example. So this video is the kind of data that can be collected from a PIV. You can see that it seems to be an important activity around like the four first guild, but it seems to be less important around the fifth guild that is almost not opening. So it can also be pointed out that the flow doesn't seem to be exactly linear. It tends to create some little vortices just in front of the guild. So I record these kind of videos for 5 of the spiny dogfish that we had in the lab. And that came from the video. So once I got good videos of the PIV, I used the MATLAB software and a package called PIV Lab to analyze them. So this is the kind of graph that the PIV analysis gives. These are the results for only one shark, it's shark 5. You can see with the color bar right there. So the color bar, in fact, is the magnitude, the velocity magnitude of the particle coming from each of the 5 gill slits. The bar is in millimeter per second. So the first picture, this one, show that it tends to be more activity around the first 4 gills, with these 4 circles characterized by orange-red color. And we can relate all of these little red-orange circles with the peaks and the other graph. So for all four first gill, you can see that the flow is slightly higher compared to the last one that tends to be like the lazy one. So if we take a look on all the data I collect for the PIV, it is interesting to regroup them in a box plot to compare them for all the 5 charts I did. So again, we can see that the first 3 gill slits work together with an amplitude of velocity magnitude that looks the same. The fifth one, again, is poorly working compared to the others, but surprisingly, the fourth one tends to be also different from the others. So to sum up, what I can tell you so far is that this mysterious fifth gill, there is an important difference in terms of morphological measurement. Its vertical length tends to be bigger, but the width tends to be smaller than for the others. Also, the flow coming from this fifth gill slit is really less important than the one coming from the 4 first. It is also noticeable that the distance between the 4th and the 5th slit tends to be smaller than the distances between the other gill slits. The 5th slit is also more arched and surrounded the pectoral fin. So that might, in part, explain why it is not working as the 4 other gill openers. So why have 5 gill slits if the last one is not even working at its maximum? The answer could be in the way that these animals are feeding. The spiny dogfish is in fact use the suction and ram behaviors to capture and manipulate prey. And what is interesting is that there is a paper published by Goto and collaborators in 2013 about the carpet shark family. So as you can see on these 2 pictures right there, they demonstrated that the 5th gill slit, which is also slightly different in terms of morphological measurement, is used during suction feeding action. This uniquely large 5th gill is in fact used in a functional way to discharge water during the feeding action of these sharks that are also suction feeders. So I think that is one hypothesis that can explain the difference in flow velocity of the fifth gill and the spiny dogfish. But to conclude on this hypothesis, I think that further work has to be done on feeding ventilation. So it would be interesting to do more PIV analysis on sharks when they are actually feeding on prey. And also, I began to work on high-speed videos of the shark ventilation cycle to be able to design a 3D model that would give us a great look on how these animals are actually using their gills during their ventilation. So to do so, I recorded videos from different perspectives of the gill opening of these sharks. Thank you.
So I'm really interested in this interaction between the gill opening and the pectoral fin, because if you look at most bony fishes, like that's where the gill opening is like right up against their pectoral fin. Do you have any insight from watching these guys breathe in terms of, do you see any interaction between that valve and the pectoral fin?
You mean if the pectoral fin is moving or something, or?
Yeah, or if like the valve interacts with the pectoral fin in a particular way.
It's not, the fifth one is so almost not moving when they're breathing, so that might be something to explore.
Right. Thank you.
Thanks.
Any other questions? Like, did you see from fourth gill slit, was it pretty regularly sort of spewing out the dye as well, or was it sometimes?
The dye was always for the fourth one.
For the fourth.
Yes, the dye was never as colored than the three others, for sure. Because in each videos, the first and the second one, there was always a lot of dye coming from these. The third one, not always, but usually yes. But the fourth one was always slightly colored than the others. But that might be because of the distance. I'm not sure. That's the problem.
So do you think that there's a possibility that they can sort of regulate which gill slits they're using?
Maybe,
like sometimes they're using
maybe because this fourth one that seems to be different, I think that would be a great thing to explore.
Thanks, Emma.
Thanks.
Sandra, you're so what was your next? So next up we have Cassandra Donatelli, who's going to be talking to us about swimming elongate fishes and how to analyze their disease.
I'm Cassandra. I just graduated from the University of Rochester and I'm starting grad school at Tufts in the fall. So while here this summer, I spent the first couple weeks watching a lot of fish in the lab swim. I like watching fish swim. And I noticed something interesting about some of our longer fish. So this is a video. This is a video of one of our folids after these spiders swimming. And you can see from the video that even though we're looking straight down at the fish, we're getting a view of both the dorsal side of the fish and also the lateral. So as he's swimming, his body is kind of rotating sideways. I thought it'd be really interesting to look at a way to measure that wobble as he's moving. So to see that, I started taking a lot of video of these fish. My setup was I had a long tank with a holding area at one end and a pile of rocks at the other end. I noticed that foliage really like rocks, so I figured if I had to put rocks at one end, they'd swim straight across, I'd get a nice view of them going past the camera. So what I would do, I would remove the barrier and the fish would swim straight across. So I got a lot of really long videos, like 1 to 2 minutes, and determined that was a lot of processing. So what I did was I chose 2 to 4 second clips of an ideal swimming across the camera. And I ended up with a lot of video that looks something like this. So this is like an ideal clip of him swimming across. Originally what I was going to do is take each of these videos, upload them to ImageJ, and measure things manually. I thought it would be cooler to bring them to a program in MATLAB and have the computer measure it for me. That way I could get a lot more points along the length of the fish, I could get a more accurate measure of the wobble as the fish was swimming. So first what I did is I converted the images, or the videos to look like this one. So they're just black and white. I still get a good measure of the width of the fish as it swims, but it's easier for a computer program to play. So to quantify a wobble, we have this equation here, where W is the width of the fish if you're looking at a dorsal view, and H is the height of the fish if you're looking at the lateral view. And then T is the measurement of the fish as it's swimming, so it's a combination of the dorsal and the lateral. The W for the big W for wobble goes on scale from 0 to 0% wobble to 1 for 100% wobble. 0 is when the fish is perfectly dorsal, and 1 is when the fish is perfectly lateral. This works out just because when distance you're measuring is the same as the width, these terms cancel and you get 0, and when the distance you're measuring is the same as the height, you get 1. So the first thing I did, I had to get all of my W's and all of my H's for each fish. The way we did that was we just ran it through the program and got thickness measurements for each point along the fish's body. That's the red line. And then we made a fit curve to make an equation of that thickness for each layer. So then we had to measure the D for each point along the fish as it was swimming. That was a little bit more time consuming because there's many more TIFF files than one. So the way we did that was first we put the midline along the fish to get all the points we wanted to measure. Got the distance at one point, and then we would switch frames, measure the new midline, the distance, the point length, and the new D. And once you did that, you had all your D's, all your W's, and all your heights, and you could get a wobble. And when you plot the wobble versus the length of the fish, you get a graph with something like this. So what's really interesting here is the max wobble and the mean wobble. The mean wobble stays pretty closer to 0 the entire time. But the maximum actually is pretty different at the tail and the head view of the fish. So what that means is towards the tail of the fish, you're getting more lateral view than dorsal view. And if you look at the video, you'll actually be able to see that this, you see this thickness of the tail here is a lot more lateral, but at the end of the video, it's more of a dorsal view, it's a lot thinner. So wobble is actually a pretty good measure of how the fish is rotating as it's swimming. I did the analysis on this for 5 individuals of African spiders, and I got some pretty cool results on that. This is the 4th individual at the top here. You can see that towards the front of the body, or right here, towards the front of the body, there's not much wobble at all, and it stays pretty dorsal. But towards the tail, and you'll see a lot of wobble. And if I play the video, you can see that that's true. A lot of thickness towards the tail end. The 5th individual is pretty cool, and actually the max wobble kind of goes in a wave like this. It goes along like. So if you watch as I play this video, there's going to be a wave that travels from the head to the swims across the stream. So it's actually a pretty good measurement of the fishes turning through the water, and it's really interesting. So I didn't just take video for Epidictes flavius, even though that's all I'm showing right now. I also got video for a bunch of other species in our lab. And I'm really looking forward to comparing the analysis from these guys with the analysis from Epidictes, because I'm guessing it's going to be pretty significantly different. Just based on observation, the lumpiness, for example, doesn't wobble nearly as much just from watching. But I'd love to be able to put it around that. So there's a lot of pretty cool applications for this this technique of getting wobble. One of them that I took some measurements on was comparing wobble to the waveform data of these elongate fishes, since they swim by passing a wave from their head to their tails. So I'd like to look at the waveform data and compare it to the wobble. And the way I would do that, this is kind of a piece, by the way. I would put a fit line along the length of the fish's body, and you can use that to get all of the wave data. So you can get amplitude, wavelength, the period, wave speed, and tail frequency. And I do have all those measurements, and I'm really excited to see how they go along with the wobble. Another really cool project that I hadn't started, but in all my endless free time, I started this another project, which is looking at the effect of tail shape on wobble. So we have lumpinus, Lycodes, and Epidictes here. You can see that they have pretty different fin shape. Like Epidictes has hardly any fin at all, whereas Lycodes is a big fin that goes all the way down to the tail. Something really cool to do would be to model that, take videos of the model, and then do the same analysis on the model that I did on live fish and kind of see how the wobble compares. The way I started to do that was I would take a look at the fish, so this is Lycodes again. Then I would idealize it, and I use a laser cutter to cut out a mold for it, and I make these rubber molds and use a Arduino servo to kind of actuate them. And this rough draft of this project, it turns out it's pretty alright. You know, it makes a wave that goes down the fish. But yeah, there's a lot of really interesting things to do with this new information, and I'm looking forward to packaging it all up into a software and like making it available for everyone. It'll be useful for not only studying elongate fishes, but you can probably use it to study pretty much any type of swimming fish. Yeah, so I really look forward to seeing how this plays out in the future. So yeah, that's it. Thanks to all you people.
Did you see any change in wobble and speed of the individual? Like the individuals are faster, or have less wobble, or something like that?
I didn't actually look at that yet, but I'm fairly confident that there would be some sort of change. I showed what I showed you was like there'd be a difference in the way the fish is moving. So the one video where the fish had like a wave of wobble, I'm guessing it has more to do with the fish's like intended direction, which is really hard to measure. But if they were trying to turn, they kind of had more wobble than if they were trying to go straight. But that's all I can really say.
Did you see that wave of maximum wobble in more than one fish? Or would you expect to if there's a traveling direction?
I just saw it in that guy. I did the analysis on 5 individuals, and that was the one I really saw it on. So that's why I pointed out it's really interesting. But I can't. I'm not sure why it's different than the others. Pretty cool. The other two individuals that I didn't put up here had a fairly consistent wobble, like it wasn't a wave, but still like their whole body turned as opposed to just the tail.
So do you think the wobble may play into the up and down courses of it? So if these guys are fish that like a steady pond, does that wobble? Because with some animals, the way that they're swimming provides them with some lift. But do you think wobbles kind of do the opposite and keeping it close to the ground?
I definitely think that wobble has something to do with the power of the fish, because if you can imagine if the tail is perfectly like this and going back and forth, you're going to get a lot of force. If it's like this, you're going to get more up and down force. But I definitely think the more wobble that fish has, it would probably be helping keep it from sinking. But I don't have any proof of that. That's just thoughts.
Thanks, Susan. Next we have John Stiles. He's going to be talking to us about puncture resistance in the skin of a whole bunch of different species. So,
I don't know if this thing will work. So I made a PowerPoint presentation when I loaded it up because I use open source stuff because I'm cheap and don't want to resort to piracy. It didn't quite work. I have lots of pictures, because I like pictures, and they didn't load. So I made a PDF. So I don't know if this thing jiggered before.
there was a way to get rid of that annoying.
I think Jonathan just put it to full
It's
screen.
full screen, not slideshow.
Yeah, but then it had that annoying transition. I found it. I don't know if
There's
there's a way to.
no way to get rid of it.
Well, I apologize. So let's get used to it. So full screen. Yeah, slideshow audio. Alright, so that should work.
Perfect.
Alright.
Oh. This is easier. Okay. I don't want to turn it off.
It's the top button.
The very top one?
Or.
Oh, there we go. Don't want to turn things off. That would be bad. So my name is Luke, and I'm from the University of Guelph, so I'm faraway land of Ontario. And I study the puncture resistance. So it doesn't cause problems. Puncture resistant skin. And this is probably my most gruesome picture. I've got gruesome pictures, but I've tried to make them not super gruesome. So I've spent the past year studying puncture resistance in hagfish. And so these are kind of a bunch of my different setups. So I don't know. I think it's really cool because, if something's going to eat you, you've got to, unless it's going to crush you first, usually there's some zapping involved. So how do you avoid puncture? So you can do it either just by being super compliant. So that means that when force is applied, you just move with it. And that's what I'm particularly interested in because I've been studying hagfish, and I think that's what they're doing. The other thing is that your skin can be really strong. So maybe it just takes a whole bunch of force to actually stab through it. And eventually, if you get hard enough, people can't really stab into you without breaking teeth, and then they have to start crushing you. Or maybe you could do a little bit of both. And so the other thing is, at what point do you say something is puncture resistant? So a lot of people go out and we have materials that we qualify as being puncture resistant, and there are industrial tests to qualify things as puncture resistant. And we usually compare biomaterials to that. So what I did with my hagfish, lovely stuff, I compared it to a rainbow trout because, okay, rainbow trout probably won't be that exceptionally great. And crap, it totally was. And so I only have the load, but it actually performed better in how far it extended at failure. So that means that it's more compliant and it's stronger than the hagfish. And then I've got this is a plastic pop bottle stacked as well. So that's better for the same thickness, but it doesn't move, which is a problem if you're an animal and want to actually get around. But I was wondering, okay, so the hagfish, they kind of get bigger, the thickness increases, and things seem to go up with that. I've got this one rainbow trout way up here. Maybe it's just if you get thicker, you're respond better. So that was one of the things I was interested in. The other thing I wanted to look at is what kind of effect does freezing have? So with my work back home, I always used fresh tissue, which made it really difficult when I had to do more than one dissection in a day. I really wanted to take advantage of the number of animals that we had here. I was really hoping to get hagfish here as well. I tried, didn't get them. That's okay, because I got a whole bunch of other stuff. I got pillage freezers. I got to do a whole bunch of other stuff. And I'm hoping to try to figure out a way to quantify being puncture resistant. I don't know how well I got to that. So to do that, I did some puncture tests, and I took skin from 20 different taxa. Some of them caught with the same net or trawling, and then some of them were from the freezer. The sharks, I don't know whether there's a SUXK that washed up last year, and then I don't know where some of the other sharks came from. But they came from the freezer. So that was enough for me. And so this is actually me skinning my last animal. So this is probably one of my least gruesome dissections because it was a little tiny fish like this. And then as opposed to the SUXK, which the tail was like that, if not more. And then I put them into these mounts. This is a mount that I brought with me and I stabbed my hagfish skin with. But it's kind of big, so I made it hard for these little guys to fit in there. And Adam had this other mount That at first I was like, I don't know if I like this, and then it turns out I loved it way more than the mom brought with me. So I'm gonna have to go back home and try to see if I can bootleg this and stab some hagfish with it. And I use some insect dissection pins as my stabbing implement. These are kind of like villiform pieces of a little kind of needly teeth that are really good at stabbing to things. And just in case, you know, the tip was getting damaged, I was using a needle. So there's a whole bunch of dissection pins that are still good as dissection pins, but not good for what I want to do with them. So what I get from my material testing system was something like this. So this is actually the contrast between the biggest things and some of the smallest things. In fact, the smallest things I had. So this is the 6 scale. And I stabbed that in my mount that I brought with me, and I had to modify that with twist ties to make it fit, because it was super thick skin. It's like almost a centimeter thick. It's a lot of skin. And you can see it has these 2 peaks. And so this first peak is actually where it broke through the top of the skin, and then the middle part of the skin, it just kind of slid right through. And then there was a second peak where it came out the other side. So I thought that was kind of cool. Didn't do much more with that because I only had the 1 6 scale skin. But the smaller mount, I could only stab a centimeter in. And so the issue I ran into now is that to make it fair, I say, okay, I'll just take my 10 millimeter point. 6 scale actually punctures at around 11 millimeters. So in the context of what the rest of the stuff, the 6 scale does not functionally puncture. But you know, something with little tiny villiform teeth like this probably wouldn't be going after a 6 scale anyways, unless it's some sort of little, maybe a parasitic thing. And so then I've got my Liparis, which is my new favorite Telios, and my Alorhynchus flavus, which was the smallest thing, and then the Liparis, unfortunately, was the least strong fish skin, which disappointed me. I had high hopes for it, but I don't think that's its fault. I think that's my fault. So what I did for the freezing is I took some Ambiotoca lateralis from surf perch. They're kind of my nice generic fishy fish. They've got pretty decent sized scales, but they're not super heavily armored. And I took some from the freezer that had died during seining. I had also killed some and stuck some in the freezer. And then I killed some and then skinned them right away. And so I got this comparison. So I didn't get a difference between the two. But I think in the future, you have to be very careful about freeze thaw. And I know I've done stuff where I've frozen things and it was totally fine. And another time when I hagfish, the notochord actually shot out the sides, and I don't know why, but freezing did weird things. So when I still took my frozen skin, I tried to be careful and make sure that it was, you know, the skin wasn't obviously falling off, because that's so good. So then I went back and I went, okay, I'm going to plot all these, the extension and the load that this fails at. Versus how thick the skin is, because you're still getting to the, you know, as I make it thicker, is it harder to puncture, which makes sense. If you've got more material, it takes, you know, a little bit more work to get through it all. And so this does not have the 6 scale on it, but the 6 scale, actually, the load that it fails at, it puts it about right here. And then I put my elasmobranchs, because I had 2 other ones, in red. And so my hope with a regression line like this was to say, okay, all my trials from one taxa appear above this regression line, because it was significant. And then I could say, okay, maybe this is a way to qualify something as being puncture resistant, so that we know, you know, there's this general trend of you get more material, you're thicker, and it's harder to stab into. But if all your points are above this line, then maybe that means that you are a puncture resistant thing. However, I've learned here that have to account for the phylogenetic relationships of things, which was very exciting because I've never done this before. And so I've only kind of half done it now. So this is I did a phylogenetic construction. I went on GenBank and I got 3 markers because I went, hey, all of my species, they've got all these 3 mitochondrial markers. This is great, except for one squalus, which has 1 marker in the entirety of GenBank. Made me very sad. And so then I used Mega to align the sequences, and Stacy ran through this with me again yesterday. It was super helpful, because otherwise I would have been banging my head against the wall. Also, the Beast website does no longer work, at least for me, anymore, which also made things difficult. So with my information, with my squalus having 1 marker, it gets to be the outgroup of everything. And I was so, if I had hagfish, it would have been even better, because they still would have been the outgroup to everything. Because the hagfish has a whole bunch of genes in there. So what we did, well, Stacy suggested that I swap out another SUXK. And then you get a kind of nicer looking tree. I don't know too much about phylogenetics, but from what Stacy had said about where things should be on this one, those kind of, they worked out in this. So then, what I did was, so I'm not going to get too in depth about what I do with phylogenetics because I'm not quite sure exactly what I did. There are R commands, and it gave me these outputs. I don't really know how to interpret them. But so I did plot them down. You get these branch nodes, and this is a reconstruction of the ancestral states. It's saying, okay, the ancestor should have been like this, and how does this change as we progress to the phylogeny? At least that's how I understand this. I'm sure Jonathan is going to know that's not how that works at all, Jonathan. But I actually wasn't expecting things to fall out the way that they did. I still don't like this tree because I'm not familiar enough with the code to correct the things that I did with the rest of my analysis. So this includes the SUXK data in there, and actually the data, the value that putting in there for that its fail force is actually lower than what it is, because that's just the end of the curve at the 10 millimeters, which it hadn't punctured at yet. And then one of the other things is that my gastroceos, those sticklebacks, they are armor, they have armor plating on them, and I would definitely look at them and say, you know, that should be an animal that is puncture resistant. And I did some hand wavy stuff before I constructed this tree, and I threw an interaction term in with species along with thickness to see how that changed. And I don't know how statistically sound that was, but I went, you know, why not? I'll try this and see what I get. I wouldn't rely on it, but I was very sad to see that that actually decreased the effect. I think the other thing is that I didn't post this up here, and so I plotted also extension and then thickness. Sharks have thicker skin, and I don't know if that was necessarily true of all the sharks, is that how thickness is related to the length of the fish. Because I did do that, I didn't put that plot up there, because I looked at it and went, no, they look pretty consistent across. So even these really small fish, they have pretty thick skin compared to other things. And I ran a regression on it, and I really should have put it in here, and we're going to get, that's okay. Because it was significant, but it was this really, really, really shallow slope. So I still think that's really interesting that these small things have relatively thick skin compared to everything else. And that could just be, you know, as you get bigger, there are less things trying to eat you. And I mean, there's been lots of people that are starting to look at fish skin and its ability to withstand puncture. And I've gone out and looked through the literature when I was doing my hagfish stuff, and there's surprisingly more literature on puncture resistance in produce skin than there are with fishes, and that's for shipping purposes. So if you're doing stuff, you don't want stuff to break. So in conclusion, freezing really didn't have too much of an effect. You know, what I figured as you increase thickness, you do get an increase in the force it takes to puncture. I wasn't expecting it to increase with the extension that it failed at. I thought they would be inversely related. So I think the next step to be to take these tissues and kind of do some histology on them and see what's going on, because the literature on how fish scales are supposed to be avoiding puncture is very different from what I found in how hagfish are doing it. Going through and just actually removing the skin, there is way more diversity in just the feel, qualitatively, the feel of the skin and how easy it is to remove it, that I think there's a whole bunch of different mechanisms that if you just do what I've kind of done, it kind of gives you this wish-washy result. There's more than one way to skin a cat, I guess as the saying goes. And so I would like to kind of do some future work and refine my phylogenetic method a little bit, and then see if I can better qualify things. And this is a picture of that Paris little snailfish. I'm really excited about them because their skin feels exactly like hagfish skin. And mounting it in my skin mounts was just as difficult. So there's something about these guys, and talk to Mackenzie about it, and she's going to tell you more about them, but they're very hagfishy. So I'd like to, these are a bunch of people, and I realized, you know, I didn't thank the University of Washington for letting me come here from Canada. So these are all, yeah, they were very helpful actually in that. So this is all the the Friday Harbor crew. Lots of people, I borrowed tools from them. They let me take tissue. Some of them actually skimmed tissue for me, which was great. Made my life a little bit easier. And then these are my Guelph crew. So Doug is my advisor, who in the middle of my exam said you should apply for this course right now. I'm going okay. And then Steve Wilson and Matt Cornish helped me build some of my apparatuses that I brought with me. And I did use my little skin map that they helped me build. And then Sarah Shorno is the grad student I work with. And while I was here, she was sending me some papers that were very helpful. She was on fixation, because that's how I did some of the hagfish stuff. So she helped me, lots of moral support, even though I'm across the continent, which was very nice. So I think that is my presentation.
I might have missed it. Did you test for different locations on the different fish bodies, or was it all
So I didn't test for different locations. Ideally, I tried to take it from the right side, just behind the head, so it'd start just behind the pelvic girdle or pectoral girdle, and then above the lateral line. However, like with some of the sharks, I got it from the tail or the head. And so there's definitely going to be a difference in different parts of the body. I did not look at that. And I think where you've got more of your vital organs, you're definitely going to have more enforcement. And I know that from the hagfish, that where all their vital organs are, their skin is a lot thicker. And people have done other work with that, but generally where you're most vulnerable, you tend to be a little bit harder to stab into. Yeah, I think more work should probably be done on that. I don't know if I do that. Because I've actually taken from different parts of the animal, and I just kind of made sure I was always comparing those parts to work around that. I don't know how effective that was. This is all my USB stuff that I can steal back. Yeah. What are hagfish? What eats hagfish? So people are on the list. Marine mammals and seabirds. There have been a couple documented cases of them turning up in elasmobranchs and other things, but the papers that they came from, I'm pretty sure they caught them because they were scavenging on something that the hagfish was inside of, and the hagfish was just an extra treat. But so what spawned my research was actually a video of a whole bunch of sharks attacking hagfish and none of them being successful, and they ended up coming away with like no holes. But I think I'm going over time. So. Well, probably. It's hard to say if the slot, because they have to be bitten first, is what I figured. It's contact with the skin that stimulates the slot. But we can talk about this one case. Because I love talking about hagfish. That's for sure.
The really cool thing is trying to cut you off.
No worries.
So next we have Kate Galloway, who's going to be talking about this cool structure called the Bomar in the Okinawa County Lab. So,
so my name's Kate, for those of you who don't know me. I'm at the University of Rhode Island. I'm a PhD student there. But today I'm going to be talking about the performance of teeth in the Ophiodon elongatus throughout ontogeny, during puncture and draw, and the implications that this has for the mechanics of vomer and premaxillary teeth. So right here is a picture of a vomer. For many of you probably don't know what a vomer is, but a lot of hexagrammats have teeth on their vomer. I'll go further into this as I go into the presentation. So just to introduce the lingcod, lingcods can get massive. So Ophiodon elongatus can get up to 72 pounds a lot of the times in Alaska, and they can honestly be as big as a person. And so this poses the question of how do such large fish like lingcod eat other large fish. These lingcod eat pretty much anything that can fit into their mouths. And if you look into their mouths, you can see teeth-wise they have a lot of options. So here's the vomer right here. There's obviously teeth on there that you can see. So the vomer is attached to the neurocranium by a layer of cartilage. It doesn't move, it's stationary. And on either side, it's a little hard to see, but on either side there's two bones called the palatine bones, and they also have teeth on those.
There's teeth on the pharyngeal jaws, back in the pharynx, and there's also teeth, of course, on the premaxilla and the dentary. So with all this teeth in the mouths of the lingcod, they have a lot of options on how they can feed on the prey. And then this is just a nice SEM photo of a vomeran tooth, so you can see this nice curved structure. And so back in 1988, Norton published a paper in Science showing that Asymanthes taylori actually uses its vomeran teeth to puncture snail shells. And so he looked at them feeding Asymanthes taylori, and he showed that they, by strong dorsal hyaloid movements, they actually push the snail shell against their vomeran teeth and to create a puncture in the snail shell. But that was 1988, and nobody has really looked at vomeran teeth in feeding besides that I found. So the goals of my project were to determine the forces necessary for teeth located on the vomer and premaxilla to penetrate prey, to determine if there's an ontogenetic shift in tooth performance of Ophiodon elongatus, and to hypothesize the possible function of vomer teeth in Ophiodon elongatus during puncture, which can also be termed during capture, which can also be termed as puncture in this case, and processing, or unidirectional draw, which I measured. So my methods. So I dissected out 10 vomers and 10 premaxillas from lingcods, which ranged from 205 to 836 millimeters in standard length. I took a bunch of morphometrics before dissection and then after dissection with the teeth. I chose 3 prey items per vomer and premaxilla. I used Cyanogaster aggregatum because we had a ton in the lab. And I euthanized them right before I put them on the material testing system so that the muscle components were compromised. I then printed 3D boxes to attach the premaxilla and the vomer to them, and I attached them with hot glue. And then I used the MTS to measure initial tooth puncture force, and I used the Amada digital force transducer to calculate unidirectional draw. So it's important to note my methods that obviously initial tooth puncture force was right as one of the teeth were pressing into the prey, and then for the unidirectional draw or lateral force, the teeth were fully embedded into the prey, and then I pulled on it at a 90-degree angle very slowly until the prey began to, the prey's flesh began to tear. So for the vomer, I made sure all the teeth were embedded into the prey before I calculated or measured unidirectional draw. For the premaxilla, as you can see here, there's 2 or 3 big teeth on the premaxilla that I made sure that were embedded into the prey, but all of these other teeth were not involved. So, my results. So, this is head length plotted against tooth puncture force. All variables are log transforms. This is just a regression and interaction effect. And you can see that there's clearly a change with ontogeny. So as lingcod get bigger, there's more force needed for the tooth to puncture in the vomer teeth. And as lingcod get bigger, there's less force needed for the teeth to puncture prey items in the premaxilla. And so this is really interesting. And if I look at the lateral force, you can see basically the same exact trend going on. So from looking at this graph, if more force is needed for the prey to escape in the larger lingcod for the vomers, then you can hypothesize that the vomers are being used to basically hold on to the prey during feeding. And this can be the exact opposite for the premaxilla. So more force is needed to tear the flesh in the prey item for the premaxilla at smaller, younger lingcods. So the premaxilla is probably functioning as holding on to the prey in smaller lingcods. So this is a really cool ontogenetic change that I found. And so there's still more stuff to look at. So I'm going to take you back to the first picture. And here, this is a smaller vomer, and you can see that there's a second row of teeth beginning to form. There's sort of little nubs in this vomer. And then we look at one of the larger lingcods, the largest lingcod that I
there is a second row of teeth actually fully formed almost around the bone marrow. So they do increase their tooth number as they grow, which I haven't looked at the effects of that throughout ontogeny. And this would also be really cool to look at with X-ray. So X-ray moving morphology in Beth's lab would be really cool to actually see what teeth are doing what in the mouth of one cod. And those are my results. And I'd like to thank my advisor, Cheryl Wilgan, and Wainwright Endowment for funding for me to come here, and Adam Summers and Laura Ferry, who are both on the committee, who I can actually talk to face-to-face, not over Skype, and the rest of the teaching staff, Misty, Stephanie, and Stacey, Ian, who also helps me quite a bit, Nick Goodmark for allowing me to cut open his large lingcod heads, and the rest of the professionals. You have multiple trials from the same structure. Did you take that into account, or might you consider? Yeah, so I did take that into account. So I also looked at the differences between the mass of the prey, and there's no effect on that statistics-wise that I looked at in R. And then also I made sure that the force wasn't increasing. And many of the times, actually, the force sometimes decreased or increased. So I made sure that the force wasn't increasing as I went on and on the function. I didn't know if there was any effect. And the teeth actually fell out. I air dried them for about 24 to 48 hours before I put them on. Yeah, so they're pretty strong.
Do you notice any wear on the teeth after you were treated?
I didn't notice any wear, but this is, the SCM photo is of the tooth after I stopped it a couple times, so back. So that is a photo after I stopped it a couple times. And I don't notice anywhere, but that's a possible.
Do all of the teeth have that same curve?
Yes, all of them have teeth. The premax are a little bit more, you can see right here, they're less recurved. They are recurved to a certain point, but they're less recurved, especially the two, there's 2 or 3 right here that are the large premax teeth, and they're not as recurved as this tooth right here.
Check my list. Who do we have next? Andrew. And so we're just going to move right along through our break. I think we put those breaks in.
You get no breaks.
So,
Pendulum. Oh, sorry.
is it the ASO?
Yeah.
Okay. So, yep. And then, so,
watch that for a second and enjoy that. Okay, so I'm Andrew. I just graduated from Cal State Fullerton. I'll be going to graduate school there under Dr. Peg Tran. So as an undergrad, we were looking at the presence of hyperostotic bone in rampiform fishes, oarfish, or braided-fish. And that kind of generally got me interested in fish bones in general, particularly acellular bone. Acellular bone and cellular bone, very different. Our bone is cellular. There's primitive fish that have cellular bone. The most obvious difference is the structure. You see cellular bone here has this very laminar matrix with no openings like cellular bone, which have these lacuna that have these osteocytes. They're particularly used for sensing mechanical structures on the bone that are used for modeling and remodeling the bone, so repairing it essentially. What interests me is that the most derived and successful groups of fishes have acellular bone that don't have these cells embedded into their skeletal system. So I came here interested in learning more about the differences of the mechanical features of these bones. And I had some ideas, and I brought them to the teaching staff, and I'm pretty sure Adam shot them down immediately. But he had a great idea of building a pendulum to simulate high strain on bone. I was like, great, how the hell am I going to build a pendulum? So I took a few days, well, not a few days, I 3D modeled the pendulum myself, started to build it, and this was my initial one. So it's very petite, has my little electromagnet here that I spent quite some time stripping wire to get as strong as I could. I was very proud. I wanted to show Adam. He came over, kind of furrowed his brow at me, looked at that. That's not going to work. So I went back, scaled it up, did some tests with some actual weights beforehand, broke some bone, figured out kind of the mass of the bob of the pendulum that I needed, and figured out the size. So eventually I came to this meter by half a meter pendulum, much more impressive than my petite one. So now I have a bob that Adam built for me, about 123 grams, connected to a servo here that was programmed to move 90 degrees to pull on this neodymium magnet here to release the bob, just swing right between the supporting arches that I printed out with the 3D printer. So once that was built, I was finally able to start collecting samples. Previous work on acellular bone was done with the Maxocephalus polyacanthocephalus, and I wanted to use the cellular bone of the Oncorhynchus shaitcha, which is the Schmitzian that we have here. So these were connected by staining at Jackson Beach. I used about 3 of them due to their large size that we had. And then 3 of these we had frozen in our freezer that I used. And I wanted to use the opercles of the opercular system just because that bone received a lot of high strain rate during suction feeding, and I thought that was optimal for a pendulum to simulate. So these aren't to scale, but you can obviously see these are very different in shape, and these were much larger. So I wanted to have samples that were identical in size, and there was no variation. I didn't want any variation in my sample size, in my size of my sample. So of course, I used a laser cutter. I made 4mm by 15mm samples of each of my bone. And to really understand if this was the correct method to cut bone and to not cause more damage to the bone than I might have already, we did SEMs. And as you can see, it made a nice cut without causing any more damage to the inside of the bone. So once we did that, I was able to go with more samples and cut everything that I needed to go and move forward. The next part was actually conducting my Sharpie impact test, which essentially is having your sample cut with a notch, being supported by 2 supporting arches, which are here, and having the bob swing through and break it. So after that, this is the actual test runs. And to calculate the energy that is absorbed by the material, all you really need to do is calculate the height of the initial bob and the height afterwards, and that's the energy absorbed by the sample. With the energy absorbed with the sample and the cross-sectional area of the broken sample, I can determine the fracture energy, which is the energy it takes to break sample. So these were the results of those fracture energy tests calculations. And this is slightly higher, but it wasn't significantly different. I pretty much am attributing that to my low sample size. So with more of a sample size, I can pretty sure there will be a difference. There should be a difference, and there will be once I have a larger sample size. So I'm hoping there is. So for soon, hopefully in a week, I'll be coming back here, getting a lot more samples, running the test again and again and again, a lot more data. And I would also like to have more species of the different bone types to see how they differ as well. And something that'd be interesting too is comparing fishes to other vertebrates to see how their bones compare to this fracture energy. So thank you for Adam for all his wisdom in helping me develop this, because there's no way I would have been able to do this without him. And Misty for encouraging me to do this wonderful experience. And Stacy, Stephanie, Ian, wisdom as well, helping me. And Ian for Nick for providing the sculpins when I need them for trials. And then the rest of the fish class for just support. Thank you.
How did you create a notch in the bones?
Oh, I also used the laser to cut the notch.
Okay.
And that was 1 millimeter by 1 millimeter.
Do you know if the freezing of the bone of the salmon might have had any effect on its strength? Or could it, or did it, you think?
It's possible. That's something I need to go further in testing with. So it could, but I'm not exactly sure at this point.
How did you get the live spoons? How did you get the live spoons? Were they from live critters?
No, they were from live critters. That data was collected from live critters that we had in the lab that I euthanized.
So do you think that it's not a possibility that they have the same work to fracture, even though it's cellular versus acellular bone? You think that they're definitely, with more samples, you're definitely going to see a difference? Or do you think that maybe there's a possibility that the cellularity doesn't matter?
It's possible. I think it might be more of the structure and how the matrix is laid out, which is something that I could actually probably model and test. I think I would prefer to have more samples before continuing and looking at that. I think I'm giving a more clear idea of what I would need to look at next.
Aside from the salmonids, what other cellular bones?
More of all the primitive fishes, salmons, trouts, copaids, herring.
You're saying does that also include fossil forms?
That's a very general term I'm giving here.
Can you define the primitive fishes? So we have an idea what you're talking about. Open gardens?
Yes.
Sorry.
Open gars, no salmons, copaids.
It's like an advancement exam.
I'm not going to answer you.
Would you expect different results changing the axes of where you're putting your notch? In other words, if you're going at it from different X, Y, or Z coordinates?
Yeah, so the Charpy test is where you actually have that notch facing away from your bob. And there's also a test where it's called the eyes-on test, where you have your notch facing the bob.
I'm more referring to the fish, whether you're taking the bone from a lateral structure or perpendicular to it, or if you're going, say, top to bottom, how you're taking your sample, which way the bone is oriented in the fish. That's going to make a difference in the strength.
That is actually very interesting. I had not thought about that. I'd only thought about the auricular bone in the string, so I think that is actually something I would like to look at soon. But I'm not sure exactly.
All right.
So I miscalculated and thought we were 15 minutes behind. We're actually right on schedule to have a break. I think the next talk is Catherine's at 11:30. So I think if we want to break, we can take it. Let's
verify that for a moment.
Catherine's up next, and you're scheduled for 11:30.
I think we want to keep on time because there are people tuned in
Okay.
who who are looking for particular.
I see. We're just cheerleaders. Yeah.
Follow up. Make sure. Sister was late. Hello.
Yeah.
I think it's working. Things on the YouTube link, right?
It is. You need to go to my Google Plus page to find it.
Ah, okay.
Or my YouTube page.
Okay.
If you went to that original YouTube link, you then have to click on my name to get all the ones that are popping up.
Gotcha.
But it's there. It's just
Slightly hidden.
it's a giant pain in the butt. I'm freezing.
So are we ready to go? All right, we're gonna do our symposium. Everybody just turn to their seats. Keep things moving along. Right. So next up we have Catherine Gordon going to be talking to us about her Jawzall. I'll let her tell you what that means. And so I'll turn it over to you.
Hi, I'm Catherine. I'm an undergrad at Cornell. And my project was to make a Jawzall. So the Jawzall is essentially almost like a model of a shark jaw, as close as you can get on a power tool, using a Sawzall, and thus Jawzall was born. So I'm going to pass around a couple of the blades that I used. They're pretty sharp. Just a heads up, as Cassandra discovered, does it cut through flesh? Oh, yes. So we know that sharks saw, or many sharks saw upon prey capture immediately post the initial gripping and grasping bite. There's a head shaking movement, and so this will create a strong motion along the teeth. But, you know, we're really not sure. We know it works, but we don't know if it works more than once. Shark tooth replacement is on the order of 25 days, and for a good-sized shark, that's nothing. You know, they can go 25 days without eating in some cases. So, are they single-use teeth? And then, are there, as you'll see on the blades that I've got, there are a lot of different shark tooth morphologies, and are those going to vary the effectiveness of the sign? And then from there, if it does, can we extrapolate some feeding ecology and feeding ecology from that? So I took a DeWalt 385 Sawzall, and with the incredible, tremendous help of Jeff Brash, who's right over there, who built this fulcrum system, and I glued using a quickset epoxy, which is surprisingly strong, by the way, shark teeth to blades from, or Sawzall blades from which I had ground down the teeth. Those were 12-inch bimetal blades designed for use on wooden nails. And I had 4 species of teeth within the scope of this project. The SUXK, which are the larger teeth that you've got over there. The tiger shark, which are the smaller ones you've got there, the silky shark, and the sandbar shark. So the two carcharinids have quite similar tooth morphologies and are, for the functional purposes of this, mostly interchangeable. And I took both upper and lower teeth from the SUXK. And so one of the really, really cool parts about this project in this class is that I actually got to take out the first row of teeth from the SUXK myself. That's probably the coolest day of my entire life. And that's why they're on there, because I got to like go down and do it with the scalpel and whew. And then the awesome of Adam handed me a bag and said, "These are tiger shark teeth, have fun." So I got a whole bag of, I think, 55 teeth there, and a couple of carcharinid jaws that I soaked and then yanked the teeth out of, also by hand, which was a pretty neat experience. Really gets, I can also tell you firsthand that these are shark teeth. And then once gluing the teeth onto the blade, getting the blade into the saw, and then onto that system, you get to actually make a cut. And so because the Sawzall goes up to 3,000 revolutions per minute, we filmed this on high-speed video at 420 frames per second. So, and this video here is 1.5 minutes long at 420 frames per second, if that gives you any idea of how incredibly speedy this whole process is. So, I mean, just looking at that, you know, it's a complete blur in your eye without having it slowed down. And due to the speed, you'll notice a huge buckling of the center. Yeah, and so in general, as you can see, it kind of gets stuck here. A lot of the time, the teeth do get stuck around the point of the spinal cord. We decided to saw into chum salmon from King's. They came headless and partially eviscerated, and floating flesh, obviously. And essentially stuck them on the board and then stuck the saw over them. Saw what happens. There's a gap in the board through which the saw can articulate. And they're held down with some nails, which you can see here and here. And that is a lead block also used by Kimberly for her power tool stabilization. So, but then, you know, you've got a whole bunch of video of shark teeth sawing into fish. So what do you do with it? So the performance metric here was distance traveled per area cut. So again, for each reciprocation, the blade is going to move both this way and this way. And one complete cycle there is 5.7 centimeters. And then it's also going to be simultaneously moving downwards. And the rate at which it travels downwards is varying based on the medium through which it is cutting. So again, when it gets stuck at the spinal cord, there's a major halt and it sort of pauses there. And it's quite cool to watch because, as you probably saw there, you can see the moment that it finally breaks through the spine and just slams through the rest of the fish. So, are these single-use teeth? So through one use, or not necessarily are these single-use teeth, excuse me. What's the difference between the species here in the first use? So from what we can tell here, the falciformis teeth are extraordinarily effective relative to the Cuvier teeth and the Chrysaeus, the six-gill. So carcharinids clearly are very good at a single cut. But then, as we look at it through multiple uses, the carcharinids lose effectiveness rapidly. Sample size here was 5 to 6 cuts, and I mean, the jump here from under 100 strokes per unit centimeter squared to over 500 was quite outrageous. And then if you take a look at the trend across trials, there's really not as much evidence as expected for the teeth being single use. I just threw a quick best fit line on here, and there's not a whole lot. There's some decrease, but as lower value here would imply, in fact, a more effective cut. One interesting thing to think about is that with the blue ones, there is evidence that the tiger sharks, the coupe, they're feeding every day. If their tooth replacement, I'm not totally sure what their tooth replacement rate is, but I can't imagine that it would be every single day. And so if you consider that with the fact that they're feeding daily, then their teeth should continue to be effective, and that is what we see. So you'll notice also on the tiger shark blade that there is a broken tooth. This happens pretty regularly and does support the low use hypothesis. The teeth broke generally on the first or second run when they did break, and when they did, it was usually in the region of the jaw that was around the location of the spinal cord. There's no way to, or there's limited way to calibrate that prior to the cut, but it's interesting to think about. If you have such spine damage to the teeth, then it would definitely require constant replacement. So there's a lot more to do with this. There's still some challenges with blade wobble due to the high speed at which the blade articulates. And so we've tried a couple of things, gluing a balancer to particularly heavy SUXK teeth. As we saw, they're very large teeth. But still, sometimes we end up with something like this, where the blade comes down onto the board instead of in this nice gap here. And then there's also trying to get a biomimetic force. So due to the structure of the setup that we had for the majority of the data presented here, we were working at about 25 newtons, but actual bite force in a shark is in in Cacarius at least, it's upwards of 1,000 newtons. In a small shark, it can be in the vicinity of 100 to 120. And so with some handy-dandy guide blades and a lot of zip ties, we can get it to about 114 newtons downwards on the blade about here. But clearly this is not the best setup. So there's still some work to go, and there is definitely a distinguishable difference between what's done, or the rate at which the blade saws through the fish at 114 newtons, and the rate at which it saws through at 25. And then there's also varying the substrate. So as you saw there when I quick snapped it over, and have probably heard, we got the chance to assist on the seal necropsy yesterday. And so I probably shouldn't be smiling like that, but I was a little bit dazed at the moment. It was kind of a... so that's a small part of the seal that we... About halfway through this cut, we switched from 6-bill to tiger teeth, and that just smoked through. Super duper thanks to Stacy and Jean-Luc for holding this little guy in place. And there'll actually be more of these available to us for next week, so hopefully I'll be able to come back up for that. He chose quite the time to walk in. Anyway, so I wanted to thank the teaching staff here in the fish class. It's been really amazing. And especially a thank you to Stacy for hours and hours of super duper late night. Press the camera, hold on to the blade, press the camera for, oh my goodness. Thank you so much. And Jeff Gratch again for building that setup. It's been outstanding. Steve and Ruth Wainwright Endowment, my advisors at Art College at Simon's Rock, and the fish class. It's great. I feel like I should move it back to this picture of the seal to ask questions, but save that. So.
So, do you think that if you had, say, 2 blades coming from either side, that maybe the shark doesn't necessarily to get all the way through the principal column. That instead, it's taken off the flash on the sides, and maybe it just comes away really easily. That you can break some of the vertical column. That at all.
You know, I'd actually be most curious about that in the 6 skill because the 6 skill teeth, which are gone, but the 6 skill teeth, the lower jaw teeth really closely resemble the upper jaw teeth, which would imply that they would possibly be able to have a sawing function. I've used them in saws and they're very effective. And so with the carcharinids, the lower jaw teeth truly are not idealized for sawing. They're definitely puncture oriented. But that's definitely not the case with the 6 skill. Yeah.
So a lot of these teeth aren't the same depending on where you're going to draw. So don't pay attention to what's sort of on the board side of it. So what do you think like having different shaped teeth can do, like along the society?
In something like the lower jaw of the 6 skill, it's cool because some of them do look more grasping oriented, and then there are sawing ones. But as far as differently shaped teeth in the jaw, a decent number of them are pretty uniform. The carchariniid teeth, I mean, I tend to put them down in a fairly decent order, but they're pretty much indistinguishable from each other. My guess would be that there would be a combination of a grasping and a sawing if you had multiple jaw morphologies, or tooth morphologies in the single section. Yeah.
Did you factor in how sharks often move side to side? Because I know the blade is just going down, but sharks usually are sawing more on the side.
So the blade, as it goes down, articulates forward and back.
Okay.
So the idea of the Sawzall is that, yeah, it provides these revolutions that are 5.7 centimeters. And so that's the sawing motion.
One more question. So in sharks, they usually bite first and then shake, right? So there's like already a puncture wound. How do you think that would change things? There's already, the blades were already in it before it started actually doing that.
You know, that's an interesting question. You definitely wouldn't see the same buckle that we're seeing here. Yeah. So due to the nature of this, we had to start the saw prior to the drop into the fish. That's really interesting because if you've already got the teeth in there, then you're going to have, I think, yeah, much less of a buckle of the fish as your initial sawing moves it. So it's probably going to create a little more stability, a little less energy lost to trying to keep the fish in place if you're already gum deep in it.
Do you think it would happen? Because it kind
How do you think the fight with these sharks be?
I'm not sure. Is there a bite shake release in the ones you're referencing, or is it just a bite release?
Well, I think bite shake release.
Yeah. So with the bite shake release, then you bite in, you shake a little bit, and cut through the material, and then the release is once you've gotten through the substrate.
It eventually ends up being just likely damage you.
Oh yeah, that's got to be absolutely important. You know, the more that you damage it, the less it's going to wiggle, and the less work you're going to have to do. True. So tiger sharks actually do gnaw on turtles, from what I've heard, and I'm really curious about that. Yeah, that's.
Unfortunately, we get to sorry. Next, Captain, today with more. Students aren't leaving campus just yet, so we'll touch base soon. Next, we have Mackenzie Derringer, who will be talking about the Halo snailfish, or the Halo snailfish, and some modeling she's been doing.
All right. Hi, I'm Mackenzie Geringer, and I am a first-year grad student at the University of Hawaii, working with Jeff Drazen. And I'm part of an international collaboration of scientists that is looking to understand life in our planet's ocean's deepest zones. So I'll get to the robot later, depicted here, actual size, and we'll talk about why I built the model. But first, I want to give you some background on the Hadal Zone, on these trenches. So trenches are the final zone in the ocean from 6,000 to 11,000 meters. They're located at subduction zones worldwide, and the one that I'll be talking about most today is the Kermadec, right here, to the north of New Zealand. And then, of course, you've all heard of the Mariana, and I'll also be showing some data from the Japan Trench. And I know that we all have seen the diagram and understand that this is a deep number, but just to further hammer it into your brain, this is 2 kilometers deeper than K2 is tall, K2 or Everest, and 220 times, or 220 50-meter swimming pools stacked in a row. So Olympic athletes that swim 10Ks, it takes them about 2 hours. So we're talking about a lot of water. And with this in mind, of course, there's some sampling challenges that come up with getting to these deepest zones. So we use a lot of free vehicles, such as this, which is a camera lander, and this vehicle here, which is a baited trap. And that gets around the problem of having cable that's so long that it actually breaks under its own weight. So trawling at these depths is extremely difficult. And the use of free vehicles helps us get around that problem. How the vehicle works is it has a weight pack that's on the bottom, and this part here is an acoustic release. And then up, actually down there, you'll see that there's a float chain. So we're able to call the vehicle back after it's been on the bottom for 12 hours or so, and then it will release its weight and then come back up. It takes about 4 hours to come back up to the surface and pull us from depth. So my research really focuses on this Hadal snailfish, which are the planet's deepest living fishes. And they're really interesting. You wouldn't think that this would be your perfect deep sea fish. It's not what you think of when you're thinking of that big, toothy, glow-in-the-dark thing that we all think of as this idealized deep sea fish. But the Hadal snailfish are incredibly successful in at least 5 different trenches. And so I'll be talking today about Notiloperis canadensis from the Kermadec Trench, that one off New Zealand. And one of the first things that you notice when you bring up these fish is that they sort of start melting right away as soon as you cut open the skin. And they have this gelatinous layer directly under the skin that you can actually see in the video. This here is the muscle of the animal, and then they have this kind of clear gel. And I'm interested in what this is and what it's for, because it's certainly a little bit odd. So I started in some of my undergrad work looking at it from a proximate chemistry perspective, saying, okay, what's in it? That'll help rule out some of the hypotheses. And we found that it's really, really high in water content. To give you a comparison, this 97% water compares to normal deep sea fish muscle tissue, which is about 80% water. So really, really high, and just a little bit of maybe a kind of fibrous tissue in there. But sodium and potassium ion concentrations, as well as osmolality, indicate that it's mostly extracellular fluid. So, which begs the question, what is the advantage to having this extracellular fluid swishing about in the body? And so I then wanted to approach the problem from a more biomechanical angle, saying what are the costs of having this fluid, or is there even maybe a benefit to filling your body with gel? Does that help you to swim a little bit farther? So I started approaching this problem from looking at video data of the Hadal snailfish here, and comparing that to a shallow water relative that we find just in the tide pools out here in Montreal. So this is Leperis florae, and this is a straight swim that I filmed. And then I analyzed these videos and compared things like tail beat frequency, body lengths per second, and then some of those waveform data that Cassandra was talking about. So these are the results here, and you'll see that the tidal snailfish does swim faster than the hadal snailfish in terms of body lengths per second, but they're also using more of their pectoral fin strokes. So these are a little bit hard to interpret because you do have some size differences and differences in life history patterns, but this maybe gives an indication that the hadal snailfish is not as efficient of a swimmer as the tidal snailfish. So to really test the effects of this gel, I built this robotic model from a couple of different materials, one of which is the front half of the robot is made from a 3D printed scan that we took on the ship after we had freshly caught some of these fish. You do this thing called photogrammetry where you take a bunch of photos from different angles and then put together a 3D model. So I'll pass this around. This is one of a print from the model. So I printed a larger hollow version of that and then cast different tails. These two are the same. They're in a silicon rubber to represent the white muscle that's along the back of the tail. And then it's powered by a servo motor battery and a little Arduino code that has it swim back and forth. And then the skin around the tail is a commercially available latex bag that I filled at different volumes to test the effects of gel in the animal on its locomotor capability. So I brought it with me today. This is the robot. And I don't really like running him out of water because it causes some strain on the motor. But if you want to have a look, come talk to me later. And these are the results from swim tests with the model. You'll see that with the gel layer, the robot actually swims much, much better. Swam at about 0.07 body lengths per second, which is about half as slow as the hadal snailfish. And then without the gel layer, you see it's kind of even struggling to move forward. So these results tend, to me, seem to indicate that there could be an advantage to having this gelatinous layer in the tail in terms of locomotor performance. So conclusions that we can take away. First, one of the big lessons out of this project was the value of a physical model when you're working in a system that's extremely inaccessible. It would be very, very difficult to bring a hadal snailfish back up from depth and run experiments on it. If you gave me, I don't know, like $800,000 in a year and 3 weeks of ship time, maybe I could do it. But this is faster. And so I think that this hypothesis of gel increasing swimming efficiency is an interesting one and worth further investigating. One thing that I'd really like to do is look at the material properties of the gel under proper temperatures and pressures, because it would be unwise to assume that it's behaving the same way at atmospheric pressure that it is under a whole lot of water. But the model seems to show that even if it is just water, it could still be beneficial. And then I'd also like to test different gel volumes and consistencies with the model, and then maybe do some work in the flume looking at how water is flowing around the tail when it's at different volumes. And then Cassandra's model is really exciting to look at an alternative metric of swimming performance, because with that you can process a lot more video and do it a lot more consistently. My analyses were done in ImageJ in that frame-by-frame measuring technique, which works, but I think it would be great to have a much better way to do this. I'd also like to look at scaling trends. In the tidal snailfish, I did find that there were differences as you looked at larger fish. In the hadal fishes, we have a problem with depth of field because you can't really tell if that fish is small because it's far away from the camera, or if it's small because it's actually small. And you can get a sort of sense of that, but it's really hard to quantify. And so I'd also like to look at some additional species. I had 2 species of hadal snailfish, maybe 3. There's a taxonomic debate going on, but 2 at least. One from the Japan trench and one from the Kermadec trench. And then it would be nice to have another tidal snailfish or another even one that lived a little bit deeper. And so, with that, I have a lot of people to acknowledge. It takes a lot of people to do deep sea research. And so I'd like to especially thank Adam, who convinced me that I could build a robot, and then Alan Jameson, who all of those lovely videos of the Hadal snailfish come from his lander work, and then the rest of the Hades team, as well as the fish class, the TAs, some of our outreach team on this last cruise for their images, and of course the captain, crew, and the captains and crew of these 5 research vessels. And I will open up the floor to any questions that you have.
So in the actual fish, is the musculature connected to the skin at the end of the tail? So
yeah, so the gel actually is concentrated a little bit farther forward on the animal than it is in the robot. And by the time you get to the end, it is mostly just muscle. So that the model that's going around is what the white muscle looks like, because the gel has already disappeared by the time you get to the photogrammetry. So that's actually a pretty good indicator of what's muscle compared to what you see the full fish looks like in the water. Yes?
In the type of snailfish, so you've got the gel and you get some fish in the type of snailfish. Is it just a muscular tail, or what?
It's just a muscular tail, but excitingly, there's a gap between skin and the muscle. And Jean-Luc, I'd like to talk to you about slip force and how that plays into these being hard to bite, because even as you're cutting them with the scalpel, and this happens on the Hadal snailfish too, is you can kind of slice at them and not make a cut because the gel or the skin is just slipping. So they have a spot for it, but they don't have gel. There are other species that have gel, though. This isn't purely confined to the Hadal snailfish. You actually see it across a number of families, including some other leparids, like the Paraproctus species, which is that one up there. And I will let somebody ask. Did you have me?
Yeah. Oh. Is there a difference in the amount of muscle in the Hadal versus the tidal one snailfish, or is it just that they have the same amount of muscle, but the Hadal one also has gel?
I tried to look at length of tail because they do differ. So taking preanal fin length as a percentage of total length, and I tried to get at that question that way, because it's hard to have the volume of the animal in situ with the gel. What I'd love to do is get actual gel volumes, and get percentages of white muscle to gel, but it's difficult to do.
You deleted the others. So our last presentation is Matt Keeble, who is going to be talking to us about some of the sticky fishes that we have here at Shannon Harbor, mostly
Kind of all of them.
All of
It's
them.
a little more comparative.
Comparative sticky fishes.
Yes. All right. So, hey everyone, thank you for staying this late. I know I'm the last one, and you're all probably a little tired. Hopefully, I wake you up and keep you stimulated with some really exciting pictures. I'm expecting some oohs and ahs when you see them. And so, I was looking at suction in these fishes, not suction feeding. When I'm talking about these sticky fish, I'm talking about the ventral adhesive disc that some fish in this area have. that allows them to stick to various surfaces in the marine environment. And so this right here is an SEM picture of a lump sucker, which I'm going to talk a lot more about later. And so one of the more common, or better, I should say, well-known sticky fishes in the area is the SUXK and the northern kingfish, right there. And it's a lot of research that's actually been done on this fish, especially here. And some work done by Dylan Wainwright, Adam, and a few others found that this fish is really good at sticking to surfaces of varying roughnesses, and that they're actually better at sticking to surfaces that are more rough and smooth, kind of like John Luke's head. And it turns out Petra actually just published this paper that shows that they're actually also really good at sticking to these really foul surfaces covered in biofilms. And the clingfish is now on the cover of the most recent version of JED, which is really cool. But clingfish are not the only kind of sucky fish we have in the Pacific Northwest. We have at least more than 10 different species that have these ventral adhesive organs, one of which is the Parasflorae, the snailfish right here, and the Pacific spiny lumpsucker right here, which is the Eumicrochromoscorpus. And so these fish also have these different, adhesive organs that let them stick to these different materials in the environment. And it turns out that they're actually better than the clingfish at sticking to these surfaces. So some work done by Dylan Wainwright and Adam shows that the snailfish can actually tolerate higher stress values on these surfaces of varying roughnesses when compared to the clingfish, which is pretty weird. And in his dissertation work back in 1967, Druderita found that the lumpsucker can support almost 850 grams of weight per centimeter squared of this area, which is almost 400 grams more than that of the clingfish. Granted, this is on a smooth glass surface, which the clingfish aren't really great at, but that's still a lot of weight more. So this is kind of, for me, this was really surprising because when I think of the clingfish, I think of this fish that's, it's in the intertidal zone. It's right at kind of the interface between land and water where you have waves crashing in and it has all these forces it has to deal with. So I kind of assume that that fish should have the strongest disc, it should have the largest adhesive forces, whereas the lumpsuckers and the snailfish, which are found in a little bit deeper waters, kind of subtidal but not quite at that interface where you have the pounding waves, that they would have lesser forces. But I was wrong. And I was like, well, why am I wrong? What's going on here? What's the difference between these fishes? So I decided that I wanted to figure out kind of what were the differences between the adhesive discs of these three fishes. And so here you can see the adhesive disc close up to all the fishes, and you can see that they're actually pretty different in structure. I mean, the lumpsucker and the snailfish are actually, they're a lot more closely related to each other than they are to the clingfish. Their families are only one node away on Muir's most recent tree, where the clingfish are actually a lot farther away. But you can kind of clearly see just by looking at it that, okay, they don't look the same. So I was like, well, what else is different about them? You know kind of what the microstructure of the clingfish looks like, but what does the microstructure look like of these discs, the lumpsucker and the snailfish? So we went out and we nightlighted, and we collected some lumpsucker and snailfish just down by the dock here. We took it back to the lab, and I dissected out, snipped out this adhesive organ, and we prepped it, and we put it in the SEM. And I was fortunate enough to get some clingfish samples that had been pre-prepared by Dylan a few years ago, one to me by Petra, which I'm really grateful. And so I stuck them in the SEM, and I took lots of pictures. I'm like, what's going on here? What's different? And it turns out that these discs do have different structures. So over here is the lumpsucker disc, and the way this disc is set up is that on the interior edge you have these really large pads. And then between the large pads and the rim you have these smaller, medium-sized pads that kind of fit in and fill in space. And then around the whole edge of the disc, you have these fimbriae, either one or two layers, kind of stick out and surround the disc, which is different than the clingfish, which only has the fimbriae around the posterior edge of their disc, and around the lateral and the interior sides that have these pads, which also tend to increase in diameter towards the middle of the disc, although the big ones are a heck of a lot smaller than the lumpsucker disc. And then the snailfish is just completely different. It doesn't have small pads and it has no fimbriae. It just has a rim with these really large pads you can see around the head with your naked eye. So they're all very different. And if you look, you can see, okay, the surfaces look kind of different. So you can zoom in at an individual pad, and this is a small pad of a lumpsucker, and you can see, okay, wow, they do look pretty different. And you can zoom again even further and look at the individual papillae that make up each of these discs. And in the lumpsucker, you have these nice geometrically kind of blocky hexagonal shaped papillae with space in between from your disc, which is a heck of a lot different. And the clingfish has these papillae which split into these really fine microvilli, which is also very different than the snailfish, which has these nice conical, large shaped papillae. And so how does this structure relate to the differences you see in the performance of the disc was one question that I was thinking about while I was taking these pictures. And when you have a suction disc, if you pull up on the suction disc, the disc fails where the outside edges slip towards the inside, and that lets water in and the disc will fail, or air in depending on where you are, and the disc will fail. So one way to prevent the disc from failing is to have, you want to increase the friction around the edge of the disc so that it's not as easy for that edge of the disc to slide in towards the middle. And so what it seems like is happening is with the lumpsucker and the snailfish is that their papillae are much wider diameter, which means they have, per papilla, you have a lot more surface contact with whatever surface they're sitting on. So that's a lot more friction, so it's a lot harder to pull up in the disc. And they're still pretty small. I mean, the average diameter of the lumpsucker is about 9 microns. You get about 6 microns for the snailfish, as opposed to these little guys at the top, which are only about 2 or 3 microns in diameter. So you have a lot more surface area to work with, a lot more friction. But that might not be all that's going on to describe how why these discs are so much stronger than the clingfish. And so I took some clear and stain images, specimens from Adams Museum, and I took pictures of them. And what you see here, this is the clingfish, is that you have these lepidotrichs of the disc, and they're nice and calcified. But then you also have this cartilaginous tissue that extends the rim of the disc. And so the cartilaginous tissue is a lot more flexible, which is good for the edge of the disc because you want it to form to the surface you're sitting on. And if you pull up on that disc, it's a lot more flexible, so you can lift up the disc more and you can create a larger negative pressure on the disc, which is good for suction. But if you look at the other two species, bones of their disc and their pelvic areas you have no cartilage, they're all ossified. So instead of having these nice flexible things that you pull up, you have these really rigid supports in the roof of your disc, which are going to resist bending when you lift up and will tend to keep that disc in that shape. And so I think these are kind of might be some possible explanations or hypotheses for why these discs are so much better. There's no data comparing the snailfish and the snailfish and lumpsucker, so that would be a really cool avenue to test to see which between these guys is the better. You don't know that yet. And so while I was taking these pictures and thinking about the structure of the disc, I was thinking, okay, well you have these discs, and all the fish are actually they're all good at sticking to the surface. They form these really tight seals. But if you're really good at sticking at something, how do you unstick? And it turns out that we actually do know how this works in the clingfish. So between the interior edge of the disc and the posterior edge of the disc, we have these gaps right here. And what turns out what happens is, Adam and a few other people figured this out, the fourth lepidotrich is actually rotated 90 degrees. So these arrows are pointing to the gap between the two parts of the lepidotrich. What happens is when they abduct this lepidotrich, it opens a gap in the disc and water can flow in, and the disc will fail, and the fish can swim off. And so that's really neat, but that's not how the disc is not arranged the same way in the lumpsucker or the snailfish. So how does that work? So I decided I was going to try and figure that out. So what we did is we have our nice setup here. We put the fish in here, and we got the camera and we stuck it up as close as we could so we could really see what was going on with the disc. And then I took some dye and we squirted it around the fish to see what was happening, where the disc was failing, where the water was flowing, and the fish was detaching. So now I'm going to show you a really quick video of the lumpsucker detaching, which is really cool. So, what you're going to see is before this plays, it's really dark. Perfect. All right, so what's going to happen here is you're going to see this is the interior edge of the fish. And right before the disc fails, you're going to see it's going to have duct, its circular cavity, and its pectoral fins. And you're going to see right here at the very interior edge of the rim, you're going to see a dark line where the dye goes under the disc. And then very soon after that, you're going to see the dye just flow from the anterior to the posterior end as the disc is kind of peeled off. And so I'll play this and explain to you what I think is happening. So what it appears is happening is that the fish is lifting, it's taking in water, and it's expanding its purples and its pectoral fins, and using this to kind of brace itself and fail that very anterior edge of the disc. And so when it does this, it fails that anterior edge of the disc, and it's just like peeling a suction cup off the wall that you have like in your bathroom. So you peel it, you lift up that edge, and you fail that edge, and so you can have water that flows in now and fails the other part of the edge, and you just have a wave of muscular contraction that goes down and pulls the disc, kind of peels the disc off, just like we did. Play that one more time. It's really awesome to watch. So it's just showing there, it lifts up, and boom, it's off. And that actually appears to be the same mechanism in these snailfish. So I have a video of these snailfish, which is also pretty cool, but there's something different in this video that I think is really exciting and I want to show you. So what you're going to see in this video is you're going to see the dye is going to, dye is going to come and it's going to form, it's going to go around the disc and surround the disc because the disc is sealed right now. But right about here, you're going to see the dye is actually going to start to leach into the disc. And so you'll see it goes in right kind of where the pads are. But then right before the disc, the fish lifts itself off, you're going to see that dye gets forced out of the cavity of the disc. And so what this video seems to imply is that before the fish are detaching themselves and failing that interior rim, they're compressing the volume and squeezing some of that water out of the disc. By decreasing the volume of the disc, that makes it easier for the disc to fail, so that in failing that interior rim, they don't have to pull up as hard of the muscle there, because the volume is less. So, like this is also exciting. And so you see the dye gets sprayed in here and surrounds the disc, which is right there. And then right about here, you'll see it starts to leach in. It goes right between the pads. So it's in there, and then it gets forced out, and then the disc fails in the anterior posterior direction. That's some of the dye leaking in from the sides of where it already was. So that's really cool, and that might be happening in the lump sucker too, because these guys seem to have very similar mechanisms of expanding the pectoral, or abducting the pectoral fins and peeling the disc off. But we need to get more high-speed video of that to really try and quantify exactly what's going on. I'm really excited to maybe hopefully do that. If anyone else wants to, because that's really exciting, I think. All right, so why does all this stuff matter? We know all this stuff about the discs now, and morphology, how they work. What's the big deal? Why do we want to know? What I think is cool about this is now that we know a lot of what's going on about these discs, at least as far as the structure, we can take these and we can apply them to models, like this super simple model here. And you can add the different components that make up the disc. So you can add the fimbriae, pads, and the rods to make up the rim. And you can kind of tweak these. You can say you can take away the fimbriae, or you can change the rim. And you can use these, and eventually you can really kind of start to tease out what is really important for a disc. And why would you want that? Because these biologically inspired discs, if you could model this and make a really good model, it could be really useful for things like suction cup, or your shower caddy, or your GPS unit, or even for a tripod for a camera that you want to go out and stick in a tunnel zone for get the time-lapse series of what's happening. So a lot of really cool, useful things with that. I want to leave you guys with the thought of making an awesome biologically inspired suckerfish model. So with that, I would like to wrap up. I want to thank all the teaching staff for all their help, and the TAs, especially Ian, for his insights for the dye and the video. And with that, any questions? Yes?
So any hint at all, I know in the invertebrates and forms that attach quickly, there are dual gland systems to do that. So one is doing the attaching along with all the fancy structure,
The musculature and
and
such.
another is actually being secreted. Well, usually epidermal cells, two different cells to break it.
So you mean like a mucus kind of?
No, it's well, exactly. But it's a releasing. It's a different cell.
So it would be like an oily kind of material.
No,
Or
let's see, so you have two single cells, and within there they form secretions.
Okay.
One of those secretions causes suction, causes adhesion.
Gotcha.
The other one releases that adhesion very fast, so that a worm will adhere quickly and will release just as quickly. And I know I've looked at a lot of, I mean, I love this whole program in suction. But most of it, we've always looked at the physical characters, and I just wondered if anybody had looked at the epidermal secretions as a possibility.
To my knowledge, no one has yet. Actually, I don't have the pictures here, but on the inside of the disc, if you look at it, in the lump sucker, you can see these really nice epithelial cells, and then you have these pores in the middle, which I'm not really sure if they're mucus cells or secreting cells, or they could be out of blood, but maybe they could be neuromass. And if you look at the clingfish and the snailfish, they have a lot more. It's a lot more kind of like papier-mâché mesh of epidermal skin, which looks like it could have some pores, but you can't really see those. You really have to kind of slice away to look in. But I think that's a really interesting avenue to look at the different compounds that they have under their discs that could be involved in sucking on something. Yes?
What about putting a macro lens on high-speed video and filming the fish? Not only implanting itself on glass, but pulling loose and having a very high-speed macro.
That would be, I would love to do that.
Well, that has, I think, a 1 to 5 macro lens that'll go on the EOS camera that'll film video.
That would be a really interesting way to kind of really get a nice high-speed video.
The other thought I have is use acrylic or Lexan, put it on the mill, and rough up the surface and use various surfaces. And then you have to polish it, of course, afterwards, and seeing what that variable surface is doing to the suction zone.
That would be really cool to do. That sounds like a really exciting test. And I think the sucking fish are really awesome. I get really excited about them. So that would be something I would love to try that. If you want to work on that.
Sure.
Yes.
Well, now you see the differences in mechanisms. How do you relate that back to the time?
Well, I would say that at least clingfish, when they're, hold on, let me take a moment. With the release mechanism, let's say for the clingfish, it moves around a lot, and it moves all the fish move around a lot, but it's in an environment where it's kind of sometimes out of water, and that's a tough question to ask, to think about. But I would imagine that these fish that are, they spend more time underwater, you want to have a more tight seal around the disc, so having a continuous ring around your disc might be better for forming a tight seal underwater, and so you don't have any opportunity where, even if you have the fins exposed, you might have a tiny little bit, which if you're maybe above land in air, you might not get as much flow inside, or with the water, you might not get as much flow into the disc if you're the clingfish. But with these guys, you really want to have that tight seal to prevent anything from getting underneath. So that could be a mechanism. But I think the differences in the release mechanism really has to do with the osteology and morphology of the disc, because the structure is really different, as you saw. So I think kind of if you could go back and look at some primitive forms of these ancestral fish to see what the osteology looked like, and maybe make some guesses as to why they evolved that way, just based off the structure of their ancestors' bones. I think it's probably might be a better way to go about that question. Anyone else? Yes?
Yeah, random study. I have a question. You said at the beginning the snailfish actually catch higher or rock surfaces. Do you remember what was the highest rock there?
I'm not sure. I think it was, they went one roughness higher than Dylan's study, so it was over 4,000, I want to say.
I think it was the same as it was in the study. Actually, we did later and with partial roughness, and I would assume that it was
That could be just because of the kind of rocks depending on where you are in the intertidal, and if you have like barnacles and the other things that are fouling up the rocks, it might be better for clingfish to be able to stick to the rougher things, where if you're down, you have these maybe smoother rocks that are covered in maybe more algae or more of a film than like little creepy-crawly organisms or crustaceans that the lump sucker and the snailfish might be better on those slightly smoother surfaces, which is we saw in George Rita's study on the glass with the lump sucker and the snailfish, or the clingfish.
we are currently a lot of people, and we are actually impressed how rough the surface is.
I would love to go out and test this on the lump suckers and the snailfish, and like put them on all the fouled surfaces and really get like a good comparison between the three species and see how they work.
That would be really cool.
Yeah, I agree. Matt, do you have a question?
Well, just more like this comment. I'm struggling with it. Like, why is he fine? It's they can all suck all the stuff and that's like
you usually find kind of like cracks and crevices in the petals, and they can change the colors a little bit to match the background. So that could be a point, but I don't think it's necessarily that much of a driving factor. Any other questions?
All right, and thus concludes the public presentations. I think it's really wonderful how many people came out to see these presentations, and I just want to thank all the people who are here in body as well as the people who've borne with us through multiple disconnections to be here virtually. You know, we've got people in several different countries watching. And so it's been a real pleasure to have all of you folks in the audience. So thank you very much for coming. We'll end now, and if the fish class could stay, we'll excoriate them for their performance. That's a word meaning they did well, right? Yes, that's what I thought.